All right, great. I probably won't take up the full time, so hopefully leave a little space extra for questions. But the topic I wanted to talk about today was A/B testing and the trends that are happening right now in the data science industry. I'm currently a senior data science manager at Tinder, and yeah, let's jump into it. So why do I want to present this topic? For one, it's not really a topic that's in astronomy. A/B testing is not, and as far as I can tell, a tool that astronomers use regularly in research. I certainly wish I had a bit of exposure to this topic when I was considering transitioning from astronomy into the data science industry. Um, it's it's exceedingly common. Anything that you build in industry ultimately needs to be tested before you sort of deploy it. Especially thinking about companies that are focused on, big tech firms and apps and so forth that are very user facing. You need to make sure that the thing works and then that it's improving the experience in some way. So testing is kind of an inevitable part to any big, machine learning or type of project that you might build. The good news is that it's pretty easy to learn. The foundations of A/B testing are very simple. You can learn that pretty quickly. And what I'll tease a little bit today and give some exposure to you is how it's getting more complex and it can scale in complexity with the latest methods that are being worked on. So what I'll talk about, what is A/B testing, some of the industry, quote unquote, industry literature that I've put together, and some trending new and best practices on this subject. Okay, A/B testing, what is it? It's asked the simple question, is this experience better? And what you do is you typically are changing maybe one thing, ideally one thing at a time. Say like you have two web pages, you're going to maybe change the color of some area, change the language of what's being talked about, or maybe just entirely introducing some new products, some new experience, targeting users for some to be able to see something, perhaps with a backend ML model. Um, so it's kind of an inevitable part, like I said, of any project. And what we're doing is we're randomly flowing users to either see, A or B experience. And that condition is extremely important to make sure that you're not biasing some population towards seeing one experience or the other, and then your results will be skewed. Another huge part of this part of the industry is defining what a metric is and what better is. So, are you looking for maybe page views? Are you looking for a conversion towards a product? Are you looking for maybe just like some subtle metric of engagement? How do you infer that someone likes something, for example? So you have to really think critically, like what is the right data to infer whether this thing is working? And then what does better mean? Is 2% a good lift? Is 10%, 20%, 100%? How do you determine what is a success for this test? And then finally, having statistical power is another huge component of this endeavor. Do you have enough users? Do you have enough people flowing through this? If you have 30 people in the experiment, 15 on each side, is that enough? Probably not. Do you have 1,000 on each side? Getting better. Hopefully you're flowing enough instances that you're getting into like the millions and into the large data sets that data scientists are more comfortable using. Some examples from where I'm working now, you might think about if you're on the app and you have a given, dating profile, we might figure out like what's the best photo that should be shown first to other people that are looking at your profile. And there's something called smart photos that does kind of constant experimentation to figure out like what should be your best photo to show. Um, Also, what is the order of profiles that you should see? There's a huge amount of work that goes into the correct amount and the best amount of people that you should see and in what order. Um, and also even down to like the fundamentals of the business. What prices should our products be sold for? Should they be increased? Are they too expensive in an area? Are they too cheap in an area? Can we use A/B testing to kind of let the data let the users tell us reactively what is like, something that they like or not like. And like I mentioned before, introducing an entirely new feature, an entirely new product, we want to make sure that it's having the positive experience that we thought it would. All right, what are some challenges? I'll just dive right in to some nitty gritty of this field. So one huge challenge to this, especially when you're dealing with things like user-facing apps where people are interacting with each other in some form of like a social network. One of the if not the number one kind of gotcha question to figure out like what is challenging in testing in that space is called network effects. And basically that is saying that if you give some users in the test, like the B part of the AB, some new experience, and there's a larger group of control users, but those users can interact with each other, right? I might give someone the background of Tinder is now blue, but they may happily interact with people in the city that they live in that are on the other form of Tinder, right? So there's some interaction happening there that's sort of inevitable, even though we did our best to make sure everyone was random. So in this case, the control users might actually see what the test users have, and the test users might actually see that, hey, these control users, they don't have the experience that I have, what's going on. And this interaction basically means that when you compare test and control, you have a contaminated comparison now. You can't just say, is the conversion rate in the test group higher than the rate in the control group? Well, maybe the control group's conversion rate is lower because they saw a bunch of people that had a weird experience. So figuring out how to solve for this is one of the biggest challenges. It's almost an unsolvable problem in a lot of ways, but there's some ways that you can apply testing methodologies to avoid it. Another challenge, and probably the broadest challenge, is speed of testing, right? In the industry, we don't have the luxury of kind of taking a really long time to study a project, and we're under pressures of business timelines and trying to get information as fast as possible. So figuring out how to get accuracy and speed of a lift of an experience in a test is huge. And this is a common thing in this industry, talking about the myth that, oh, we can plan for an idea, we can build a model, we can deploy it with engineering resources, and then do an analysis with testing. And this whole process will take like a month. In reality, and this is probably true for many industries, it takes perhaps even several months, 3 months, 4 months. So imagine if you had a project that you eventually found out was going to lift the business's, let's say, revenue or number of users by 20%, enough to pay for your entire department's salaries. What if you could get that 20% project lift 1 month faster, right? 2 months faster. So like any amount that you can kind of shorten this up is just table stakes for making your job and perhaps even the whole company a profitable opportunity. Okay, so what did I do to try to collect what is the best practices in the industry? Well, for one, I by no means am the expert of A/B testing. I don't know all of the methodologies in extreme detail that I'll mention. So instead, what I did was relied a little bit on ChatGPT. So I took over 16 of the top data science companies. I went to all of their blog sites. This is basically all public information. And I mined pretty much every article related to A/B testing from all of these companies. Netflix and Meta, Uber, Spotify does some great testing stuff. And of course, Tinder does too. And I did not read all of these articles because that would be insane. This is like 40, it's actually more like, 50, 60, 70 articles. Instead, I fed them into a GPT model. I told it to look at all of those links and links connected to those links and build a basically living data set so that I could ask it questions. What companies are doing this? What are the most common methods that all companies together are using? What are some themes that you're seeing in the literature? of what testing you're doing. So there's a lot of work that went into the conversation and the prompt modeling, it's called, of GPTs. I'm sure as many of you already know. And so that's an entirely separate subject. I won't bore you with the details. Instead, let's just dive into what I found. So the themes that I found are improving accuracy, speed, the network effects I just mentioned, figuring out how to project the A/B testing's results into the long term, and just general testing process options were the highest themes. Some of the hot methods in those themes, I know a lot of these will be pretty jargony, but I'll just kind of mention them so that you have some sense of what's out there. Difference in difference is one of the largest. I won't talk too much about it, but it's basically saying I'm going to give everyone in this, let's say, city one experience. I'm going to give everyone in that city another experience. And I'm going to hope those two cities are very, very similar to each other. And I can at least calculate how they're different so that I can adjust it. This is a way to, let's say, avoid that network effect. No one's going to interact in these two cities. Sequential testing, Cupid, multi-arm bandit, some really fun network effect solutions, which I mentioned. Diff and Diff also helps with that. Offline learning, which has a through line to astrophysics research, mainly like theoretical astrophysics, and some other subtleties of testing. The top 5 methods, just so you don't have to read all of these terms, would be like sequential testing, QPED, difference in difference, offline replay, and multi-arm bandit. And you can see some of the top companies that are using this. So if you're interested in working for one of these companies, check out some of their blogs that cover these topics. Okay, so I'm just going to flip through basically a few of these, and I'll stop at a time that it seems like we're getting bored or we want to just focus on questions. So what is QPED? I think it's pronounced QPED. It's controlled utilization of pre-experiment data. In short, what you're saying is, you know, information before you hit that start button on assigning people into groups A and B, you know how users are acting and what their behavior and their history is prior to that experiment starting. And basically it's saying you can leverage that information to hone the statistics of your comparison. So if I know that before the test, you know, I'm launching something that will hopefully make people less picky when they're swiping on the app. And I know before the test that this group of users are actually very, very picky in the first place. So I know that the sort of the standard deviation of their pickiness is already quite tight, right? Like there's an error bar pre-existing in those users' behavior. So then when I look at the comparison, I can kind of leverage that as sort of a almost like a Bayesian prior to figure out what the lift is of their behavior. So this is great for accuracy. It's also great for speed. They go hand in hand. As you increase the accuracy, you don't need as many users, which means you don't need to run it for as long. So it improves testing times. It's also very helpful when testing very rare events, which you might normally need to like get a lot of population buildup to see. Multi-arm bandit, probably the coolest named A/B testing feature. This is fun if you haven't heard of it. It's basically saying that you are going to dynamically flow the balance of users in order to capture some benefits while the test is live. So if you have groups, let's say A, B, and C, and let's say variant C is maybe they're like a really high price, a slightly high price, and a low price, let's say. And then the low price is actually the way better option. Those other two are exploring a parameter space that we don't want. It will figure out we're going to actually send some of the flow of new users into the C group to kind of capture some benefits of the better price while we're doing this testing. Now there's a balance, of course, and there's a lot of math that goes behind the right balance to figure out this sort of exploration versus exploitation balance. You know, I want to capture some benefits, but I also want to make sure I'm exploring the parameter space and still doing the test perhaps to see if the other groups are better performing over time. Surrogate outcome, we don't have time. Yeah, maybe another couple. Surrogate outcomes is pretty interesting. It's getting a little bit into like a regression, um, a regression type ML project. What you're doing is you're taking a bunch of metrics that are in your experiment. This is just some company thought these metrics were good metrics. And you figure out which one of those metrics correlate with a long-term outcome. So maybe these four metrics actually correlate really well with the total revenue or the lifetime value of a user. And so when I'm testing something in 2 weeks, they maybe can give me some signal of what revenue will be in 6 months. So I don't need to test something for 6 months to find out what the revenue will be. It's quite hard to find instances where you can do this projection to a long-term value. But when you can, it's table stakes to increase your speed and actually ensure that you're making the right decisions for a very, very long time scale. You're not just thinking of what's going to be a great lift in 2 weeks. I want to know what's going to be a great lift over the next year, the next 2 years, and beyond. Encouragement to signs. I actually think this one's just fun. I don't know of any other companies publicly that are using this besides Spotify that mentioned it on their blog. It's a way to get around that network effect issue by basically saying that we're going to give everyone the feature. So maybe this is something that isn't hopefully like a very dangerous feature that you want to introduce, but something maybe like a new area in the app, let's say. Not too dangerous, but everyone can have access to it. But only some people are going to get nudged to go look at it. So you're going to send them a little notification, an email or some kind of engagement mechanism to send them over there. And what this does is it really, really helps controlling for the user intent, right? If you give two people an experience and some people really, really like it and some people really, really don't, maybe some people would have liked it no matter what. And some people are kind of forced to have to like it because it's right there in their face. Because maybe I'm not explaining this well, but basically it controls for this very difficult thing, which is intent, which allows you to get at the causality of the feature. So this isn't just, let's say, the people that got the experience are liking it simply because, let's say, young people tend to go to this corner of the app a lot, right? And if you give that experience to young people, they sort of would automatically like it. And so you have this bias in your data set. So you don't really know if it's working. You're just kind of looking at a bias. So you can eliminate that bias by controlling for intent and trying to get the causality of, is the feature itself the thing that's good? Excuse me. All right, the last thing I'll say is simulations, which is really exciting because this is, in my mind, very similar to like theoretical astrophysics. You're like creating a universe off of some fundamental principles of physics and hitting the forward run clock to see what the future looks like. But instead of using physics as our foundations for the rules of the simulation, we're using past behavior. So I might, look backwards in time and see which people swipe very intensely, which people don't swipe a lot, which people like this thing or like that thing. And you could sort of build out some rules and conditions so that if I want to perhaps consider testing some new thing, I can just actually hit the simulation button and say, okay, I'm going to have 20% more users that are picky in this area. What would that look like? If I had picky users, what do I know about picky users? How do they behave? Let me flow that through their interactions. Extremely expensive to build this, but really, really cool. And some of a very handful of top companies are looking at doing something like this. All right, so that's the time. So in short, A/B testing, it takes a lot of statistics. You have to understand causality. and you have to have evidence-based research. All qualities in astronomy research. It's just a topic that is not that common in like observational or theoretical astronomy. It relies on the same statistics and the law of large numbers of astronomy. We want big numbers. That's where we can kind of really get at things. And while it's really easy to learn, there's a rich and growing field of a lot of complex techniques. A bit about myself, I got my undergrad at Rutgers and my PhD at Texas A&M on physical properties of high redshift galaxies, not A/B testing at all. And shout out to professors Casey Papovich and Steve Finkelstein, who helped me along this pathway. I did a postdoc at Space Telescope for a few years. Shout out to Dan Coe and Larry Bradley and the Relics team. And then some mentors, Lou Strogler at Space Telescope really helped me figuring out like how to navigate the transition. Andrew Baker. I got a fellowship at this program called Insight. And then I went straight into a startup as a data scientist, and then became a data science manager at Tinder. And I've been in that industry for about 5 or 6 years. That's it. The last thing I'll just say at the very end is that, it's not all only data science. I still like to continue my passion for astronomy, just more in my personal life. So my wife and I will go, dark sky hunting now. I've leaned into like the amateur astronomy aspect. I've joined the member of the Los Angeles Astronomical Society, and I give talks to my cousin's 3rd grade class on like what is space. So just wanted to share that there's other ways to stay involved. That's it.
Thank you very much. Any questions in the room for the speaker? Eva, anything online?
Yes, there is one question from an anonymous attendee. Do I read it?
Go for it.
It's longish. How can current Astro students better prepare themselves to apply for roles like this? What would you recommend for gaining experience knowledge in topics like A/B testing, where we may not have the opportunity to employ them in our research?
Yeah, that's a really great question. I would say when good recruiting companies will look to see if you have the skill, not necessarily the years of experience on the project. So learning the skill is still valuable, right? You can take online courses, you can take test projects, you can read about the subject and just learn the fundamentals on your own. And that's not wasted effort. I think like Meta and other companies, like they really try to get at like, can you think through how you would design this experiment, how you would look for the right metrics? That's a huge question. What is the right metric to infer if this thing is working? And I think you can study and practice that a lot. Yeah, great call up, Taka, on the companies that have all their info online.
All right, if there's no more questions for Brett, we will move on. Anna Schauer is our next speaker, data science in a small consultancy company. Anna, are you online?
Hi, yes, I am. I hope you can hear me.
Yes. And
Awesome.
I apologize for the pronunciation of your last name.
All good. So let me try to share my screen. I haven't worked with Zoom for a while, so. Yeah. It's looking good, isn't it? You can see my screen?
You can see your screen and the slides on the side as well, if that's okay.
Yeah, I'm trying to change that. Yeah. All right. So thanks a lot for giving me the opportunity to talk at another astronomy conference, even though I'm not in the field anymore. Thanks to Eva for reaching out. Yeah, hello from Germany. My name is Anna Schauer. First, a little bit of an overview of my path, and then I'll dive into what I actually do as a data scientist as opposed to like a astronomy or astrophysical scientist. So as you can see, I'm German. I have a lot of German bullet points on my CV. I did my PhD in Heidelberg. I'm originally from Munich, where I did my master's and my bachelor's. And then following my PhD, I was in Austin, Texas for 5 years, doing theoretical astrophysical research there. So by theoretical, I mean computational astrophysical research. And since about 1.5 years, I'm now a senior data scientist at Taltegos, which is a small management consulting company in Munich. So I brought you some of the shiny slides from my company, the credential presentation that they have. So why Taltegos? What does their name stand for? It goes back to Greek roots, to Thales from Milet, the first or one of the first Western mathematicians, and also to the Strategos, the Greek army leader. And this kind of is the combination of the two things that my company does. It's AI data-based consultancy. This is the mission, the right, guiding companies in becoming data and AI-driven organizations and creating value, and therefore addressing the challenges that some of the companies face, that only a fraction of companies have a chief data officer. Only a small fraction are really good at delivering their data strategy. So we are trying to help small to large companies to transition into a more data-based and AI-focused business. So, yeah. So now let's dive a little bit into what I actually do. This is an overview of the topics I worked on over the last 1.5 years. It's not all the topics. And I sorted them in this diagram kind of between how complex something is and how fun something is. And what you see here is, we have smaller projects, like you just do an analysis of some table basically, or some combination of tables where like this company goes and participates in big exhibits, and they want to see what kind of visitors came and how does it compare to their usual exhibit. We also are big in like nicely displaying data to a broader audience. So, for example, we can display the customer sales data in a dashboard. So the creation of those dashboards can be more or less complex. We do a lot of extract, load, transform workflows. For example, we write data from one system into the other system and help create a unified view on the data, and to kind of break down silos that exist either between different systems or between different subsystems in different countries. And this can get a little bit messy. So this is why this is not on a completely easy side, is because sometimes the data is just a little bit messy. Sometimes I work with machine learning, so something that goes beyond pure analysis, pure statistics. For example, predicting when customers are stopping being customers. This is called churn. So when do people not buy anymore from this company but don't announce it to you? So, or better even, when will they soon stop buying from your company? And then also one big project that we have, also in combination with a university, is called Intelligent Production Planning and Machinery and Plant Engineering. So this is really a 3-year project where we try to use machine learning to predict certain outcomes for very, very specialized, huge factories that this company is actually producing. So the company is producing factories. They have many, many different properties. Everyone is unique. And we try to predict how long it will actually take to produce those factories. And another topic is I recently had the pleasure of dividing Germany into marketing regions. So a company asked us to help divide their marketing team or to divide Germany into regions for their marketing team. And that was a fun little challenge. What you can see also is that most projects are up here on like positive fun scale. So it's nice to work on. You get a lot of feedback. You get a lot of loops where you loop back with your customer to see that you're still aligned on the topic. And rarely ever does something drop below this zero fun line. And that's usually the case when you work really hard on something and then it turns out it's not feasible for production. So when a project was more complex, then I'm more sad when it's not realized. Whereas if it was a little task, then it doesn't matter so much. But I would really say this is the downside. The not so fun projects I have are the ones that don't get realized. When I compare this to astrophysics, I think most of the topics I worked with in astronomy were harder than what I work on now as a data scientist. I worked in computational astrophysics, and like implementing something on a code that has been historically grown was usually not the most fun because it was very, very complex. Running simulations on a supercomputer can be frustrating, but it can also be rewarding once it works. Then you're really proud that such a complicated task is working out. When you decide that you would need a telescope on the moon to actually observe your first galaxies, that's also super exciting and super complex. Going to conferences is fun. And then the big thing with writing papers, I'm pretty sure you all know this famous quote, "We would like to thank the referee for the helpful comments." And sometimes this is fun to implement new ideas, but sometimes you just want the paper to get published and are dreading answering additional, more or less helpful comments. So I thought this comparison might be useful for some of you. So that the space is differently filled, I would say, for my astronomy science projects than for my current data science projects. To take you a little bit along, I picked out two of the projects I did as a data scientist and want to just show you what I did there. So I picked one that was fairly easy. For example, I was asked to analyze if my company that I work for is going to two big exhibitions, to exhibition A and to exhibition B. If like the same people go there, if people that are as important go there, if people that make a lot of revenue, have large sales, go to both exhibitions, and therefore we could only switch to going to one, or if we should like still go to both exhibitions next year, and to also compare it to how often or how many people do usually go to those exhibitions, and is it reasonable to still go to this big of a number, or to repeat the same visitors anyway? And things like that my company does with a low-code, no-code tool called NIME. And I created a little example workflow where you can see you can really nicely connect the dots, you connect the tables, you can read one table here. So this table, for example, is for all the visitors of the exhibitions. And then there's another table that's in the CSV format that shows the sales numbers. you don't want the private people, you only want businesses attending your exhibition, so you filter them out. On the other hand, you sort your sales to the different companies and characterize them into small, medium, and large. You combine them. You then deal with exhibition A and exhibition B separately. You compare it to other exhibitions, and then in the end, you can create something like just like a simple histogram showing how many visitors you had in which exhibition, and then how many of them were small companies, medium companies, and large companies. So this is a fairly easy task that doesn't take longer than a day, and a lot of the time usually goes into finding the right tables and finding the right columns or fields in those tables just to get an idea. So this is something that, yeah, sometimes pops up and is nice because it's a easy, fast thing to do. Next, I want to show you one of my more complex problems that I solved. And that was a recent thing. And the fun thing is I had to cycle back to one of my astronomy lessons and to one of the astronomy codes I've been using for a long time to solve this problem. And for this problem, I used, again, the same low-code node code tool KNIME, and then also my Python notebooks with some libraries. So the goal was to divide Germany into 12 postal code regions. And these regions needed to fill some criteria. One was that these regions needed to be coherent. So you can't have like holes in your regions. You can't like have discontinuous regions. They need to be next to each other. And then those regions need to fulfill some criteria. And that is, they need to have a similar number of web visitors, a similar sales volume, a similar number of businesses, and a similar number of private people attending, like living in those regions, so that every person from the company's marketing team would have a similar number of people to deal with, a similar number of businesses to deal with, a similar sales volume, and a similar number of web visitors. And when you look at German postal codes are 5 digits. And here you can see a small map from Wikipedia where you can see the first 2 digits. And you can see that some of those numbers are adjacent, others aren't. And now I have I think it's a total of 20,000 different postal codes, and I need to group them together, and I can't just start counting from 1 to the highest number because sometimes they are not next to each other because they are like grouped a little bit strangely internally. So I thought about this problem for a while. Thought first I could solve it with a traveling salesman problem, but and unfortunately it's just too many postal codes. You can't do that in a reasonable amount of time. So I routed back to something used in a code gadget or subsequently a repo. So the way I approached this was if I find a way to move through my map of Germany along the different postal codes, then I can cut off as soon as my criteria are reached and I have my first region, and then I can continue counting this as the next region. So I really wanted a sequence of postal codes I can map through. And this sequence, traveling salesman problem, is too large. I actually went ahead and created a Peano-Hilbert curve, which you can see here in the bottom right. The Peano-Hilbert curve is nice because it's self-similar, so you always find regions that are close in space, quite close to each other, and you can kind of zoom in and also meander around this. So I created my Peano-Hilbert curve. I mapped like the 3D coordinates of Germany onto a plane that fits well enough because Germany is small enough. And then I can walk through this curve until my criteria are met. And then I can work on manually aligning some of the borders, some of the things that didn't quite work out, because it would work nicely if this was a square, but we have some edges and we have some angles. And then this doesn't work. Yeah, and this is one of the results. So you can see here, Germany is divided into 12 regions. Let's say this is the number of businesses in each region is color-coded. And you can see that we are ranging from like 8,000 roughly to 12,000, or to 10,000 and a little bit. So we're spanning a range that I think is acceptable in terms of variation. And you can see that the regions mostly belong to each other. Now, I must admit, I can't show you real company data. So the exact terms I used here are changed a little bit. And also those are just random numbers that I assigned. And I didn't have time for the third step on those fake data. So for example, I would use those, I would cut out the most northern western part and add it to this blue region to make this region more coherent. But overall, this is how I approached the solution and what I roughly did to solve this problem. And completely doing it manually is, of course, out of the question, because then you, when you change your criteria a little bit, then you need to redo it. So that's not a good solution. So I was happy that I came up with this method and that I could use the old gadget methodology of using a Peano-Hilbert curve. So even when you're doing something completely different, don't forget your astrophysics knowledge. After like 1.5 years, you might find a problem where you can apply it. Yeah, that's it. This is the end of my presentation, and hit me up if you have any questions, please.
Yeah. We'll start online. Eva, any questions online?
Not so far, but I found it. I want to make a comment unless somebody else comes up with a question. Thank you, Anna. That was so interesting. It was really fascinating. And it sounds to me like, what would you say is the largest business that uses your company for projects? I'm thinking that in Germany, they're a little more pragmatic and probably more companies use this type of services instead of trying to build them in-house.
Yeah, but even big automotive companies sometimes need external help. So we're helping some of the big players there. And we also, like, I mostly work on projects for the manufacturing industry.
Okay. That's very interesting. Thank you.
We do have a question in the room. Oh, sorry.
Yeah, thank you for the very nice talk. I've done similar things as you as well. I'm curious that in your company mission, you mentioned that AI is also important. A lot of the things you mentioned, which I agree is very cool and fun, you still drive, you still have to make a decision on what models you're going to use. So in that way, as in the second in the second talk, we heard that that's more astrophysics. Let's say, do you have experience in your company, or are you driving this new AI in which you go and use large language models or GPT type of things? Are you guys doing something related to that domain?
Yes, we are too. It's just not my main topic, so I talked about the things that I'm most involved in, but the service plan, which my company is part of, is having a huge initiative for agent-based AI systems. for agentic. They are using a platform called Mazumi. I think you can find some information on LinkedIn about it. So my team lead is very involved in this, but I mostly, I'm more working with traditional ML, but I would say.
Any more questions? Any more online, Eva?
Nothing over here.
Then I wish you a great rest of the conference. It was fun to join remotely.
Thank you so much.
Thank you, Anna.
Here, could you airdrop it over, maybe?
Yeah, AirDrop, G Drive, email.
Just 1 second while we get the slides loaded. Our next speaker is Christine Yi, talking about building Pathfinder evaluations, retrieval, and applications for astronomy language models. She's a student at Stanford University.
Okay, not that one. And let me pull this down. Let's see. Hey, look at that. All right.
Thank you again for the introduction. I'm going to be speaking about Pathfinder, which is a tool we built for semantic search for astronomy literature, so essentially using the power of modern language models to help astronomers in their day-to-day research and literature review tasks. I mostly worked on the engineering, so I'll be mostly speaking about the engineering, but I'll also talk about some of the evaluations work we did and also the future directions I'm interested in. I wanted to highlight that I did this work as part of the Jelinek workshop at Hopkins, which is a linguistics or interdisciplinary linguistics and computation workshop hosted at Hopkins over the summer, and that I found out about this research program actually through ATDS last year. So very grateful for that, and worked with a very wonderful team across Space Telescope and also the Hopkins Linguistics Department. So what do we know about language models? Language modeling has sort of been, and sorry for the long background, I'm just going to give some context that I think is interesting. Language modeling has been like an interesting task, mostly for computational linguists, for over 50 years at this point. The most traditional approaches to this involve things like n-grams and Bayesian models, so counting the exact words that appear in text, or Google scraping all the books ever written and putting up the n-gram tables. Around the time of what people consider to be the deep learning revolution of like the early 2010s, people started applying neural methods to doing this natural language processing. For example, recurrent neural networks, LSTMs, etc., embedding algorithms like word2vec. If none of those things seem familiar to you, that's also okay. But by leveraging neural methods, we were able to go from doing just the most simple tasks, like trying to translate sentences word for word or retrieving documents based on the contents of specific words, to doing things that were sort of fuzzier, things like semantic similarity, how similar are two sentences to each other, or directly translating from one sequence to another without going through n-grams and words on their own. And also this intermediate phase of the deep learning revolution was the area in which we first started getting more general benchmarks for language model language understanding, things like being able to do specific grammar tasks or answer questions about the real world. And then finally, today's sort of large language model era is mostly defined by training very large transformers with massive spend on both pre-training, so learning basically from the whole internet, and also post-training specific kinds of techniques that get language models in shape to talk to humans, like conversationally, to follow instructions, and also to perform on open-ended generation across a wide variety of tasks. So some of the benchmarks and tasks that are sort of open questions today are that most language models are created to work on. Instead of just doing translation, which is pretty much considered to be solved, or things like sentence similarity, most people are focused on open-ended capabilities, things like solving math problems, answering questions for a user, or even writing software engineering tasks. And so language models today are capable of many things. You can do information retrieval and semantic search fairly well, for example, with embeddings, which is sort of the core of Pathfinder. I'll be speaking more about that. But language models are also capable of a lot of other things, like question answering from basically a natural language question that a user inputs, including in many expert domains, few-shot or zero-shot task learning, basically sort of do the structure of language. If you write your prompts here correctly, or if you ask the language model in a nice enough way, you can get them to do pretty much any task that's within their capabilities passably well, even without directly training for a specific task. And also instruction following, so that's sort of downstream of few-shot and zero-shot capabilities, but if you give them instructions that can be answered in natural language, they can follow these instructions reasonably well as long as you train them the right way. And so, given all these very broad and open-ended capabilities, there are obviously many useful things that we can build on top, both for the whole real world, but also specifically for scientists. Here's some examples of applications of language models in science that I find interesting. First, there's sort of the larger effort. This was mostly 2 to 3 years ago that this was super popular, but training language models for domain understanding, so projects like AstroBERT, AstroLlama, or Google's MedPalm, which is a language model trained to do medical question answering. But we found that language models that are sort of trained broadly on the internet already have enough language understanding to then be able to pick up very domain-specific things from astronomy literature, just by giving them the right data. There's some amount of interesting work on finding latent scientific knowledge in models. So, for example, Matt Tuvek is like a material science project, and they found that actually recover the structure of the periodic table and other interesting like trends in the chemistry just from the embeddings that language models directly learn. And then also language models have been generally trained to do many useful research tasks, such as math in like an auto-formalization environment, or just open-ended generation, and also code writing. And so Pathfinder is the project we worked on over the summer, and it uses large language models to index and search through over 350,000 astronomy papers, which enables a couple of really useful applications, we think, for astronomers. The first being semantic search. So instead of having to go to Google and type in like the keywords you're thinking of, or ask your colleagues around for the right papers, you can actually just ask a question directly in natural language or describe the research you're looking for, and to the best of the language model's ability, it will be able to match your question to the papers, regardless of if you're using the right keywords, if you're phrasing the sentence the right way, or if in general you're doing the right things for the Google or Google like search algorithm. The second thing is natural language synthesis. So we're able to do basically retrieval augmented generation. So language models can hallucinate. If you ask them a question about your research directly, they probably won't answer the right thing. But if you give them the right research papers in context, for example, let's say you append 5 of the papers that are retrieved by your question to the prompts for the language model, they tend to be much more factual and much more grounded in the actual research, and also able to draw directly on the papers that you give them. And finally, we create some exploratory visual interfaces for paper discovery and research trend analysis. More on that later. But first, I just wanted to highlight the work that I didn't do, but other wonderful people on our team, like Kira, worked on. Again, evaluations and user understanding are crucial to building good systems of any kind, but particularly good language model systems. And so our approach to doing evaluations was, for the user side, we primarily did Slack-bot interactions. So we had the little system for Pathfinder in the Space Telescope Slack, and astronomers could just ping it to ask it a question, and that would trigger our whole back end. And then we also did direct user interviews. I believe we did about a dozen in order to better understand how astronomers were actually using and feeling about the system. There was some more analysis done on the kinds of questions people were asking. Most of the questions that were asked in the Slack tended to be knowledge seeking, and then a little bit of stress testing and some amount of like general testing of capabilities. So in building Pathfinder, we focused mainly on the kinds of knowledge-seeking and paper-seeking questions that were useful, rather than answering sort of the edge cases. And then I'll speak more about this later, but we also had some synthetic development benchmarks that we used in order to have a fast engineering iteration loop. So again, our goal was to do literature search for astronomy in a semantic way. So we used over 350,000 papers, and the majority of the papers were published and in specific journals. I believe we got the actual index from ATDS directly, and then we scraped abstracts from arXiv. And we only focused on published papers for now, but eventually an extension to Pathfinder would be to extend this much more broadly to all the different sorts of papers and non-published writing or code, for example, that exists in the astronomy ecosystem. I believe NASA is also working on similar encoding and search systems that sort of span NASA's whole domain understanding. The basics of semantic search are here. So essentially, we have certain kinds of language models. They can turn this whole complicated document or abstract, let's say like hundreds and hundreds of words or tokens, into an embedding, 500 to 1500 dimensions. And then that embedding exists in some high dimensional space. And the most basic way to kind of take a question and turn it into a bunch of papers that are relevant to it is just to do an embedding search. So you take your question, you put it through that same encoder, it ends up in this high dimensional embedding space, and then we just look at the cosine similarity. So essentially, how similar are these vectors overall? And then that allows you to do, to first approximation, a pretty good retrieval of what the most semantically relevant papers are. The intuition here is that the encoder, or the high dimensional numbers that are being output by whatever you're using to embed it, that encoder is trained to be able to essentially output the numbers or almost features that are most relevant to the semantic meaning of the paper. And so having more similarity along those dimensions means that the things you have most similarly in embedding space also will turn out to be the best papers, at least we hope. And then once you do that, the most simple sort of setup for creating a language model response that is grounded in actual retrieved papers is to take the query, to retrieve the papers, to append them to the query with a bunch of metadata and context, and then to pipe that all into a language model and have the language model output some response for the user. And so that was our sort of first prototype of this system. This is sort of a sidebar, but it turns out even just by embedding all the papers and not doing anything on top of that, there are some pretty fun visualizations that can be done with it. Here, this is work that Karthik, who sort of led this project, did, but this is basically mapping the whole landscape of astronomy papers onto 2D space. The intuition here is we take all our 1500 dimensional vectors and we project them as closely as possible onto learned 2D space. And we get this sort of map of astronomy literature that you can segment by the sorts of experiments that are happening, for example, like where different telescopes are concentrated, but also just the different subject areas that are, I guess, like broadly under the umbrella of this conference. And then to summarize sort of all of the engineering iteration we did, our final product was to do a two-stage retrieval system with re-ranking. So I'll talk through exactly what this means. We start from the full corpus of arXiv papers, 350,000, and then we do an efficient as possible embedding search because obviously we're not trying to do sort of complicated language model operations on top of 350,000 papers. The way we do this is first we filter based on certain things, like if the user wants keywords or things in a certain time frame, or is otherwise asking for things that might use metadata filters. And then on the rest of that, we do what's called a hypothetical document embedding search. It sounds a lot more complicated than it is. Basically, to get better results, you can just turn your query, like your user question, into some hypothetical abstract. It doesn't need to be factual and it doesn't need to be correct. It just needs to be sort of in the right semantic space. And then we use that query embedding, or the embedding of the created hypothetical document, to search against all the other papers. And from that, we take a first pass top K. So our 250 or so of the best options. And then we use a more expensive operation, which is re-ranking with a cross encoder. So another large language model, not one we train ourselves, just one we get from an API that is trained directly to do this sort of relevance thing, to re-rank them. And that's how we get our final retrieved papers. And then into the back end of the language model, we give between, let's say, 2 to 10 of the most relevant papers to ground the question answering. And then for the development, this is just a quick aside about how we benchmark it. So I guess there's the vibe check, which is you look at the papers that are being retrieved and you sort of think to yourself, as an astronomer, do I think this is the right paper to retrieve? But we wanted to be a little bit more systematic than that. And so we had some automated development benchmarks that we set up. They were basically synthetic question answering. So to do to test whether we're getting the single correct paper for a given query, we basically generated synthetic queries from papers and checked that that was being self-consistently matched. And then to do questions that might draw on multiple papers, our best approximation to that was to take review articles, to take paragraphs with a bunch of citations and turn those into queries and then check how many of the citations were being pulled. The multiple paper one was a much harder one to solve, I guess because there's so much noise in the papers that review writers choose to solve anyways. But in general, we found that these benchmarks were a pretty good development signal in terms of the direction that we wanted to be going for a retrieval system, and also that they tended to work, at least they tended to align pretty well with our final benchmark, which was actually astronomer written sort of gold standard questions and answers. So questions from the users paired with astronomer responses and the papers that a professional astronomer would choose to cite if they were answering this question. And here's just a quick overview of our final system. So again, we have the metadata and we have the queries, and then we have filters for the metadata, and then we have our whole embedding search setup, so the semantic search and the re-ranking, and then we, again, pipe that into the language model. So this is, for example, depending on the sort of task someone's looking to do, if they're building a language model system, any of these things are fungible or any of these things can be replaced out, but this is what we found worked for us. And then in addition to the initial generation for the prompt, as part of Pathfinder, which I'll speak more about in just a second, we have also consensus evaluations and further, I guess, like agentic retrieval steps. So here's a look at how Pathfinder actually works in case anyone's curious about trying it. I'll also link it at the end if anyone thinks this would be useful for them in their capacity as a researcher. You can ask a question basically in natural language, so whatever comes off the top of the head. For me, that was, what is the largest mass binary black hole collision detected by LIGO? And you can set your settings on the side. For example, I was choosing to weight by keywords, so to weight up papers that had more of the keywords that I was looking for, and also to just do the full complexity semantic search. And you can see that the papers that are being retrieved all have really high relevance, which is really good. And at a first glance, these are the correct papers. They're all about 1905-21. And then, I don't know how well you can read this, sorry, but basically, we got the correct answer out of the language model, which is good. We didn't, I haven't checked, for example, if you just ask ChatGPT or something without web access, if it gets the correct answer. It honestly might, but this at least has its sources, and you can go directly to the sources also to do it. And we also have a consensus evaluation between the query and the abstract. So we ask the language model to think about whether there are conflicting opinions present in the papers and to sort of point that out to the user if there are. That was our approach to dealing with sort of fuzzier questions or more controversial questions that a user might ask. And on the right, we have that same embedding landscape of all of the astronomy papers. The blue points are the papers that are actually retrieved. And because this is such a narrow and factually answerable question, the papers that are retrieved are very concentrated in the space, which I believe corresponds to where all the black holes and gravitational waves things are located in the astronomy landscape. So some future directions for Pathfinder. The site is currently up and running and people can use it, people can give us feedback. We want to increase our coverage of use cases, increase the robustness of the system, get more feedback from users, and also expand the literature coverage. And then something else I worked on the side after finishing the initial engineering with my co-author Charlie, we worked on doing also interpretable search with sparse autoencoders. So instead of just having to express your whole desire for the retrieval through natural language, which is still like a pretty good interface for communicating exactly what you're looking for, we also enabled basically to break down the language model understanding into specific concepts or feature vectors that can then also be used to directly steer the output. So we wrote a paper on that, there's more there, and I'm also happy to answer more questions about how exactly that works. But basically it turns out that not only can you write natural language questions about the astronomy topics you're interested in, but that those astronomy topics are actually represented as directions in the feature space, and that those directions are things like, oh, black holes or machine learning, but they're not just the exact words machine learning, the exact words black holes. They're actually the whole family of semantic concepts that are related to that. And so it allows you to do like very precise edits to your query. And then these are the future directions that I'm sort of personally interested in, if anyone wants to find me and talk more about them. I'm generally of the belief that language models will continue to improve as they get new data sources and new training paradigms, and also that sufficiently large models in, the far future will eventually be able to solve pretty much any task that we can very clearly define and benchmark, right? Even if the models aren't there today, as long as we have sort of like a direct, a very clean definition of what they should be learning, I believe that they will eventually learn it. And so it would be nice, and I'd love to chat more about what other parts of our research loops can be sped up with the right tools, and how can we build those tools either for the models that we have today or for the models that will exist in the future. And also how can we apply more interpretability techniques to have transparent and reliable performance so that we can actually trust them in our scientific research. Thank you very much. I'm not sure how I'm doing on time, but these are the paper we wrote on Pathfinder and the app itself, and I'm happy to take questions.
Thank you very much. Everyone, round of applause. So I will co-organize your prerogative. I will ask the first question because I've done a little stuff with semantic search, and I think I found this paper, the August paper on. I am curious why there were so many closed weight models used. I mean, it looks like you used like an OpenAI model for the initial kind of embeddings, and then you use this Cohere, which is a closed weight model. Did those have considerable better performance than like, kind of the standard sentence transformer, kind of more open weight models that are out there?
Yeah, to be honest, we didn't really test either, for example, fine-tuning our own like embedding models or sentence transformers or trying to find open ones. One of the main reasons we use closed weight models was actually just ease of access. Like, you don't have to host it yourself. You can just sort of use it through an API, and the API is very plug and play. I believe that actually we did, like the team that, University of BD, or the team that sort of like spawned this project, did build their own encoder, like sentence transformer model for astronomy papers. And we actually found that compared to the, I guess, considerably larger and more industry incentivized models that OpenAI put out for embeddings, that we got better performance just from using sort of a canned industry embedding. For the actual generation we also tested a bunch of different models, and we found that in general, the models that are closed weight and thus have all the industry incentives were slightly better at doing the sorts of like reasoning and synthesis tasks we were interested in compared to hosting like llama models on our own.
Cool. Any other questions in the room?
Hi, great talk. I was wondering, does the current version handle erratas for papers that are published? Will it incorporate that into?
I'm sorry?
Will the current version like handle erratas for a paper if
like-
there was a correction to the paper or something? Will that be included?
We don't currently have that, but that's actually a really good idea and really interesting, especially for the sorts of like more complex questions that one might ask of the model.
And kind of a second question, how does this handle retracted papers?
I believe we don't have an explicit exception for that yet. I think as long as it's on ATDS and findable on archive, it will be on there. But I don't know that retracted papers still appear on ATDS.
Any online questions?
No, nothing on here.
Any other questions in the conference room? We got a couple. Here we go.
Okay, hi, great talk. I was just thinking about I know you started at 1990, but all of the old papers that are like, they don't have, that there's just like pictures of like photocopies. Is there like, can you deal with that, or is that like something?
Yeah, that's a great question. That's also something we thought about, especially looking at building benchmarks off some of the older review papers. They were all citing papers that were sort of out of our domain. We'd eventually like to have, I think they are on ATDS, just if they weren't on ATDS and also they didn't have an abstract on archive, they didn't end up in our final corpus. But there are like language models, or like vision language models are also capable of things like character recognition and indexing things, or like multimodally, for example. So we actually can, or if you were willing to put in the engineering effort to get those papers online, they would basically be sort of plug and play with the rest of the system.
One more.
Yeah, Great talk. Thank you. So maybe two quick questions. The first one
Yes.
is kind of related to the last one. So what about information containing images in those papers? That's the first question. And the second one is probably, I know the answer, but that really nice figure that you have, the two-dimensional projection of all the papers,
yes.
right? I assume that the axes have no physical meaning,
Yes.
or is there some meaning there?
Yeah. Thank you for the questions. To the first question, so currently we only work with the introductions, conclusions, and abstracts of the papers. So basically the sort of text that is most directly related to, like for example, authors will usually give some expository reasons for their paper in either introduction, conclusion, or abstract that is sort of most directly linkable to a query. So we found that, for example, including the full text of the paper or trying to include images was sort of noisy, as in like noisier than having just those text sources. However, you can imagine like eventually a really good retrieval system that's very fine-grained would probably chunk the whole paper and embed the images as well and be able to answer not just specific questions about the field that rely on like 6 different papers, but also questions that rely on like figure C from one paper and like this table from another paper and synthesizing that. Those are like the future directions in which we want these tools to go. For the second question, you're correct, these axes have no physical meaning. Maybe like to first order, they're like the principal components, or it's the UMAPs technically, but it's more of a exploratory tool / fun visual analysis than any sort of real statement on what the field looks like, I guess.
Thank you very much. One more round of applause. That concludes the morning session.